Hello students, in this lecture we are going to begin module 1, which primarily deals with how we represent a program uh, so that the computer would understand it. Simply put, it's called machine level representation of programs. A few definitions to begin with, some of them you are well versed with. Bit represents a binary digit which can hold a value of 0 or 1. Byte is a group of such 8 bits. And then uh, what we have is instruction or instructions, a group of them. A single instruction can be viewed as a command that we give to the computer to tell what needs to be performed and on which data it needs to perform that operation on. We are going to dwell more and more into what an instruction is, how we represent it, etc. Now, these instructions can be uh, interpreted to be similar to words in our general language. So, we string a group of words to make a meaningful sentence. So, in the same way, we uh, write a sequence of instructions to make a useful operation. The instruction set can be interpreted as vocabulary of a computer's language. It will give us some set of rules and guidelines, what's possible, what's not possible, how we need to uh, r- uh, write the instructions so that the computer would understand it. Again, program, the very notion of program is a sequence of steps to achieve some end. And here we would say that the sequence of steps would be like each step would perform one specific instruction. So program is a sequence of instructions. Moving further, assembly language is a representation of machine instructions so that we humans can understand it. It's an intermediate language that we tend to use, and typically there would be one line in the assembly language for each instruction that a computer should operate on. Machine language, or the very basic language that the computer understands, is a sequence of zeros and ones, nothing beyond that, right? And that's why it's called binary representation also. The other end, we have high level languages that again you are all well aware of. What high level language means is, like the name says, it's at higher level. It means that it is farther from the hardware. What it also means is when we are writing a high level program, we do not worry about the hardware details, means whether it is running on a uh, uh, ARM CPU or x86 CPU or IBM Spark processor or IBM Power processor, etc. Right? So we simply focus on the logic and try to get the best possible uh, correct program. Right? So that's the abstraction. Now, this again can be interpreted as an example of abstraction. What are the uses of high level language? They typically allow the programmers, us, or the end users to think in more natural language and use words which are simpler for them. So these language, the statements we write in this language can are more familiar to the humans or end users than the computer. And what it helps us is the programmers productivity would improve drastically. And if we have some complex logic to be written there is no point of struggling with the hardware details in addition to this complex logic. So that has been separated out. What high level language gives us is a flexibility to think only about the logic and how do we achieve that logic. And like I have already mentioned earlier, the programs that we write are not tightly bound to the hardware. So we can write a program and that can be run on multiple different hardwares without any loss in in its accuracy or the action that program needs to perform. So in this process, we have two other programs which are called compiler and assembler. What a compiler does is it takes this high level language and converts that into the assembly language. And what assembler does is it takes the assembly language and converts that into machine language, basically a sequence of zeros and ones. Let's look at a more uh, with an example. So let's say we have a C program, and here is just a small code for swap function, and it is taking two variables v and k. uh, the size can be the type of the variable can be anything. For now, just assume that v is a vector and k is one integer. What this swap function primarily does is it is swapping elements vk and vk plus 1, right? And uh, that's what the action that this function is performing. When we give this piece of code to a compiler, I'll remind you again, the compiler itself is a program, right? And it works on each of these lines and converts them into assembly language. And here we are taking the assembly language based on RISC-V ISA, because that's what we are going to take as an example and study further. Okay, so the assembly language for this swap high level program would sorry, the assembly program for this swap high level program would look something like this. We have some sequence of steps. uh, SLLI represents shift left logical immediate, add is add operation, LD is load double, SD is store double, and we have JLR, which is jump and link register. So these are all the instructions that RISC-V ISA provides. So the compiler has used those instructions to achieve the same logic of swap. Now this would be the input to the assembler and it would convert them into a sequence of zeros and ones. So this is how your end assembly, binary code would look like. And if you remember, many a times um, the output of your compiler is called a binary. It's precisely because of the fact that everything when it would be a sequence of zeros and ones. Okay. Uh, so here we have 1, 2, 3, 4, 5, 6, 7. So we have 7 lines of assembly code, and each of them has been converted into a string of zeros and ones. And here also you would say you can see that there are 7 lines of binary code, right? And imagine if you want to debug at either the binary or the assembly, right? So that would be a very tedious task to the end user. It was, frankly. And if you remember the generations of computers, in the very first generation, people did not, uh, till people have come with the concept of assembly, they used to write and debug programs in the basic machine language itself. Now, what we are mostly used to or exposed to are debugging and making corrections, everything at the high level. So this is the most the biggest benefit of high level language. Even it helps in the debugging and correcting the code. So the instruction set or instruction set architecture would be one of the inputs to the compiler and assembler. That's where we are binding the high level program to the some particular hardware. So each hardware has its own ISA. And typically when we say compilation, it does both compiler's job and the assembler's job. So we give a high level program, it internally converts it into an assembly language, and then it converts it into a binary language. Okay. Now, if you are wondering why we need to look at some particular assembly language, typically nobody does that. But why are we looking at the assembly in this course? Is there are very nuanced concepts in ISA and the assembly that will help us to become better programmers and architects. And I hope to convey the same by the end of module 1 to all of you. Okay. And as a student, you should learn one assembly language to know its relevance and impact on overall working of the computer. And then uh, computer languages, there would be probably few hundreds, are not as diverse as human languages. We have uh, thousands of languages all across the world, if not more, and each language has its own um, grammar, etc. So they are very diverse, but that's not the case with the computer languages, and more specifically so for the assembly languages. If you learn one, learning some one other assembly language would be quite easy. And uh, as a computer architect, when you learn the assembly language, you will understand what all uh, microarchitectural decisions were made when some particular hardware was being built, because the hardware is adhered to or tied to one particular ISA, right? And we'll understand why some decisions were taken and why some optimizations were involved, etc. And we will also understand the optimization capabilities of the compiler itself. Mind you, this the compiler here means only the compiler, not the assembler. And typically the high level program hides the runtime behavior of the programs. What it means is when you execute the program, we don't typically know what's happening underneath, right? How the program is getting executed. So learning an assembly language would help us to understand how the program is getting executed, and in process you will also be able to analyze any inefficiencies in the code. Now, when you say inefficiencies, it's not wrong logic, but rather it's about how to improve the performance of your code, of your program further. It means that how to make your program run faster, right? You can say you wrote a merge sort, and anyways, it's better than a simple insertion sort. So, are you happy with that, or do you want to optimize your merge sort further? Optimize in the sense you want to run it faster. If you have such kind of inclination, then we need to look at the assembly program of that merge sort. Also, with the latest concern of about security at the hardware, writing or and understanding and analyzing assembly programs would help us what are possible vulnerabilities and how do we stop them. So this would be the security aspect. So if you learn and study the assembly program, then it would help us first to improve the uh, performance of the program by fine tuning it, and we are also able to stop any possible security threats. Okay, now with that, let's look at some of the basic functional units of a computer. I think most of you would already know about that. uh, so here we have the input module, the output module, we have the memory module, ALU module, which is the data path, and the control module, which is the control path. So these are the five basic components. And of late, because the uh, computers have become very complex, a new module can be imagined to be there, which is trying to connect all these modules. Let's put it as interconnection network. So we still look at only the five modules as the basic modules, but interconnection network has a um significant say on the overall performance and power. Okay, why we have the memory module, and why is the control path data path separate from the memory module? So if you have that question, that's primarily because we follow what's called von Neumann architecture. It's also called stored program computer. What it means is, let's take your merge sort as an example. You wrote the merge sort program and you want to sort 1000 elements. These 1000 elements together, let's call that as data. So the merge sort would work on the data to produce another data which is sorted, right? Now, what stored program computer says is both the program and the data are sitting in the memory. Sitting in the memory means stored in the memory, right? At some different locations, and the control path and data path together would retrieve the program and data from the memory, operate on the data according to the program, and write it back to the memory. So the processing and data happen at two different places, right? And the this has been the one of the um, building blocks of almost all the computers you see in the present day. So all of them follow the stored program computer. Now, if you remember, I've mentioned about near data processing or in data computing, right? So those are moving away from the stored program computer, saying that moving the data from the memory module to the control and basically the CPU is taking a long time. Let's try to get them closer and if possible merge them. So that is a different approach, which is not yet in the mainstream. Okay, so whatever is in the mainstream is the stored program computer. Like I mentioned, both the program and the data that we expect the program to be operating upon will be stored in the memory. Now, if you ask, well, how do the stored program computer work if we are giving the elements, not may not be 1000, for example, let's say 10 elements from your keyboard, right? That's what you would have done earlier also when you were trying to test on small things. So what happens there? So what even though you are giving the data from the keyboard, it would be stored in the memory first, and the program and is anyways is stored in the memory. The data you enter from the keyboard or any other input device will be stored in the memory, and from there on it's common. The CPU will read the program and the data from the memory and work on it, right? And eventually, that same data will be displayed on your LCD or monitor or any touch screen or anything like that, right? But as such, the data that you input and the data that will be sent to the output modules will definitely be stored in the memory. So in because the memory will be storing both instructions and data, there needs to be a way to differentiate what instructions are, uh, what data is, right? And so accordingly, we need to have some guidelines and these guidelines will be provided by the instruction set architecture. Now, to identify the data, you would eventually represent any integer or floating point number as a sequence of zeros and ones, right? So I would suggest you all to revise the integer and floating point representations and how the arithmetic is performed on them, the add, subtract, multiply, etc., right? This you would have already studied in the digital logic. Now let's take a quick example on how these modules would interact in the stored program computer. I have already spoken it, but a quick visual on that. Let's say we want to execute an instruction which is add a comma b comma c, right? And what we expect that this instruction should do is it should add elements b and c and place it in a. Okay, now um, so these are the 5 basic components, and let's say the instruction add a comma b comma c is here in the memory, and the elements a b c are somewhere else in the memory given as green block. When this program is getting executed, first the instruction will be brought to the control unit. The control unit will then decode it, right? And that's when we will realize that the operation we need to perform is an addition, and it needs to be performed on elements which are b and c. At that point, the control unit signals the memory to send b and c to the ALU. The ALU now has signals from the control unit saying that it needs to perform an addition on b and c which were sent from the memory. It will add them and eventually write a back to the memory. So that's how these modules, these basic units would interact. Okay, now when we want to see the same result on the output device, the memory the control unit again signals the memory to send the same data or copy of the same data to the output terminal or any output device, and that's what would be displayed. Okay, continuing further, a few more definitions. Because I introduced you to the term instruction, it primarily has two things. One is operand. Here in this instruction add a comma b comma c, a b c are operands, and operation is given by add. Add is also called as mnemonic for addition. Okay, we add is a short form of that. So together these form one instruction. So an instruction has what operation to be performed and on which elements or which data items that operation needs to be performed. So here we can also say that b and c are input operands and a is the output operand. All this information will be stored as part of one instruction. A few more definitions. Registers, you'll come across this term very frequently in this module. For this module, just assume that the registers are the fastest and closest memory storing units, and they are readily available to the ALU. They work as fast as the ALU, right? And there are typically general purpose registers and special purpose registers. We are going to look at both of them as part of this module again. And instructions are, like I mentioned, having the operation and operand in it. There are three types of instructions. One is data transfer instruction. Okay, data transfer instruction means loading a data from the memory to the register or storing the value in the register back to the memory. Arithmetic, logic, and shift instructions that perform the operations in the ALU like add, subtract, multiply, divide, left shift, right shift, etc. Okay. The third type of instructions which which are quite new to you at this moment, are called control flow instructions. These would be branches, jumps, etc. So we are going to look at each of these by taking RISC-V as an example. Okay, and along with the other registers, we also have a program counter. Right? What program counter contains is an address of the next instruction that we want the control unit to execute. It's also called as an instruction pointer sometimes. It is just to relate to, it is a pointer to the next instruction. Right? It stores the address of the next instruction. Instruction register, on the other hand, is the instruction that the control unit and the data unit or the ALU are currently working on. Right? When we say that add a comma b comma c is currently being executed, then instruction register will have add a comma b comma c in it, and the program counter would be pointing to the next instruction following this add instruction. Now, because both the data and instructions are sitting in the memory, and we'll be talking to the memory more than often, let's try to understand how this information is organized and stored in the memory. Okay. Typically, the memory would consist of millions, if not more, cells, and each cell would typically store one bit of information, either a 0 or 1. Now, uh, if you want to know where my data is sitting, right? Let's say you have stored some one file in your hard disk. So how do we retrieve it? We retrieve it using the location or the address of that file, or address of one particular data item. It need not be a big file also, right? Here we have the notion of address of a memory location. Okay, so in the memory we have stored data and the program, and to retrieve either of them we need the corresponding address. And if we are wondering how many bits of address are needed, typically uh, it would depend on the size of the program, right? And we don't usually go and assign each bit an unique address. That will be too cumbersome. And if you look at the address, the sequence of addresses, let's say you have 1 byte, okay, uh, which has 8 bits, and if for each of these 8 bits you want a unique address, what it means is you need a 3-bit address to identify one of these bits in in a byte. So for each byte you have 3 bits of address. Now both needs to be stored in the memory, right? You otherwise you will not be able to know what is the address to begin with. So if the address space or the size of the address, right, is big, then the hard disk will be filled more with addresses than the data itself. So accordingly, the address space is reduced, and we typically do not use individual bits to manipulate. We use a group of bits. So one of the common policy we follow when building a computer would be to make the memory byte addressable. It means that for a group of 8 bits, we have one unique address. This is also called byte addressable memory. Now we know that each of 8 bytes have uh, one unique address. Let's look at how these data are organized in the memory or stored in the memory, right? They are stored typically in the form of words. Word is a group of n bits, right? If n is 8, then we would say word and byte are same, but typically that's not the case. The n is also called word length. We are going to use the term word length in next couple of lectures also, so do remember it. And why is this notion of word introduced? This is because whenever the memory is contacted, it replaces with a word of data, not a byte of data, not a bit of data. Okay, it replaces with n bits of information. And when the processor wants to write, or the CPU wants to write the data, it would typically need to send n bits of data along with its address. Okay, means the minimum transaction that can happen between the memory and the CPU is a word. Typically, the computers that we see today have word length somewhere between 16 to 64 bits. Typically, 16 would be for small embedded processors, and 64 bits, and even 72 bits for the current high-end processors. Okay, now we can imagine that the memory, whatever no matter how big it is arranged as an array, and each element of that array is having a width of n bits. So we would say the first location is first word, second word, then probably ith word, and probably this is the last word, and each word is of size n bits. Now, when we say byte addressable memory, what it means is, even though this is n bits, and let's say n is 32 bits, it means that it has 4 bytes: byte 0, byte 1, byte 2, and byte 3. And because we say that memory is byte addressable, it means that each of these bytes of this word has a unique address to it. Okay, now even though the memory is organized as an array of, or imagine it's organized as an array of words, each, if the word length is greater than the byte, then each individual byte of that word will have a unique address, and this address is what would be sent by the memory to access that particular byte. But then we are saying that the memory and processor interact as uh, in terms of words. So how does the memory respond if we send a byte address? Let's say if we send the address of B2, will it send only B2, or will it send B0, B1, B2, B3, or it would send, let's say, B2, B3, and B4 and B5? So those also can form one other word, right? Accordingly, we have the notion of word alignment. So before that, a quick example again about with a one specific address. Here we have the address 1000h. H is hexadecimal, right? Now when we say 1000h for is the address of one word, it has 4 bytes. If it is 32 bits in length, then the address of the first byte would be 1000, the second byte would be 1001, third would be 1002, and the fourth is 1003. Accordingly, the address of the next word would be 1004. Okay, each word represents 4 bytes, and each of those 4 bytes has a unique address. Make sense? Now, let's come to the word alignment problem. For an address, the corresponding data cannot span multiple words. Now, let's say the processor, instead of sending the address of the first byte of data, it has sent let's say 98h. 98h, let's say, is let's say this is 96, 97, 98, and 99. So 98h is the address of the third byte in the first word, just as an example. Okay, now how does the memory respond? Will it respond saying that it would send 98 the byte at 98th location, 99, let's say 100 and 101? If these 4 bytes were sent from the memory to the processor when the processor is requesting for the data at 98h, then we would say that the memory is not following word alignment. But if it says no, you cannot give me 98 and I will not give you the bytes 98, 99, 100 and 101, it would be said that the memory is following what's called word alignment. In such cases, what the memory does is it would respond with the data of that word itself. Okay, then the excuse me, the bytes that the processor would receive is 96, 97, 98 and 99. The memory will make sure that even though an address is given which is not to the first location of that word, it will send that entire word only. It will not send bytes across two or more more words. This is very important when we try to design the memory module. How will the memory respond for an address which is not the starting location of a word? If we take the 32-bit word length as an example, it can be used to represent any numbers or any characters. So here is an example where we are using the 32-bit word to represent a signed integer, and specifically here the sign magnitude form. The bit 31 is representing the sign and the remaining 31 bits are the magnitude. But then again, we can use the same 32 bits to represent a number in 2's complement form, or if it is a floating point, then it has its own format, etc. That's the reason I've mentioned you to revise those representations. The same word can be also used to represent 4 ASCII characters. ASCII characters, as you are aware, will take 8 bits each, means 1 byte. So 4 characters can be stored in 4 consecutive bytes of a 32-bit word. With that, we also have a little interesting uh, concept called big endian and little endian assignments. I will in to make the video short, I'll pause for now and we will discuss further in the next lecture. So basically, big endian and little endian would help us to identify the location of first byte in a word. Okay, with that I will pause for now. Thank you.